velocity is equal to f into lambda. So lambda can be written as velocity divided by frequency, right? So velocity we know as v naught ms minus 1, and then frequency we know as 5 gigahertz. So you have to write 5 into 10 to the 9 per second, and then you have to find the value of this. You will get certain lambda value in meters. So you can write the wavelength of the wavelength is lambda naught meters. And then the next question is starting with Maxwell's equations. Derive the wave equation for an arbitrary component of electric field E. Mention the assumptions clearly. So in our lecture, we learned about how to derive the wave equation for arbitrary component of electric field, starting from the Maxwell's equations. So basically, we will be using the Faraday's law and the Ampere's law to derive these equations, and also we used the other Maxwell's laws to assume that the divergence of the electric field is equal to 0. So the derivation that we have done in the lecture, I think you can refer and you can use that to answer this question, right? And then let's move to the third question. A load of 15 minus 60 J terminated 75 ohm lossless transmission line. The operating frequency is 2.4 gigahertz. Find the following parameters. The line length is lambda long. So the input impedance of the line. So we have now to draw the transmission line circuit diagram. So there's a certain load at the end of the transmission line, and we have to write all the values in this diagram, and the length of the line is going to be lambda. And let's assume actually that I will redraw this one. So we have like equal lengths on both sides, okay? And the length of the line towards the source is lambda, and the characteristic impedance of the line is 75 ohms, and the frequency is 2.4 gigahertz, and I think that's all. And we are asked to find the input impedance. So this is the input point, and the input impedance of this point is given using that equation that we learned, which is Z naught into Z L plus J Z naught tan beta L divided by Z naught plus J Z L tan beta L. So we know the value of Z naught is equal to 75 ohms. Beta value we know 2.5 over lambda, right? So beta is the propagation constant. So it is defined as 2.5 over lambda, and then the beta L value will be 2.5 over lambda into lambda, which would result in 2.5. So we can calculate tan beta L as tan 2.5, which is 0, right? And then once you substitute the 0 for the tan beta L, what you are left with is actually Z naught into ZL divided by ZL, Z naught. So once you cancel out the Z naught values, you are left with ZL, which is 15 minus 60J. You can convert this Z value to polar form, and you can do that using your scientific calculators, and you can write it in R angle theta in degrees form. And then the next question is the reflection coefficient at the load end. the load end reflection coefficient is given using this equation, ZL minus Z naught divided by ZL plus Z naught. So you know the values of ZL, Z naught, you can find by substituting these values to this, and you can find something like A plus BJ, for example, and you can again convert it into a certain polar form, and you can find the angle and the absolute value. You can do the conversion using the calculator. And the reflection coefficient at the input. So at the input, there would be some changes to the angle of the reflection coefficient. So at the input, the reflection coefficient is given by the magnitude of the reflection coefficient at the load into the angle, which is e to the power j through beta L. So the angle j to beta L you have to find, and you have to substitute here. So basically, you know the magnitude of the reflection coefficient, and you can put it as, maybe if it is R naught, you can put it there, and then you can substitute for 2 beta L. 2 beta L is equal to 4 pi in this case. So right, beta L is 2 pi, and then 2 beta L is 4 pi. So they are all equal to 0 degrees. So basically, the value of this expression will be R naught, because EJ0 is equal to 1, because cos 0 minus J sine 0 equal to 1. And next we have to find the VSWR, which means that voltage standing wave ratio. Voltage standing wave ratio is defined as the one using this equation, which is 1 plus magnitude of reflection coefficient at the load divided by 1 plus reflection coefficient at the load, which you can find by substituting the value for R, the value of R naught here. So because R naught is the magnitude of the reflection coefficient, so R naught value you can put here, and then you can find the final value. For example, you will get for R naught maybe some value like 0.7. Then you can substitute that value, and you will get some value for this. It may be point something, or sorry, it's not a point value. It's going to be between 1 and 0. So 1 and infinity. So you have to get some value between 1 and infinity here as a VSWR. And then the next question is about using Smith chart. So the Smith chart, you can actually download